Okay, so before we start these notes, we do need to go in our calculators and change the mode so that we're on degree mode, since we're going to be doing lots of problems that involve angles. So in a TI, we'll need to go into mode, and then it'll be down here. The default will be radian. So you all are going to need to change it to degrees. So when you take the IB exam and your calculator gets reset, this is one of those other modes besides stat diagnostics that you need to make sure to fix. So you'll turn it on to degree mode. And then in numworks, you will also need to change your mode. So that will be going down to settings, and then angle measure, you'll want to select degrees. Your default will also be radians on this one, so it's important that you switch it to degrees. And you can see in the top corner on the left when it says DEG, that will always be there and let you know that you're in degree mode. So to start our notes here, so Pythagorean theorem, just some review. This is not in your formula packet, so it is a formula that you just need to know. And very important note is that it only works for right triangles. We're going to see all sorts of triangles this unit, and the Pythagorean theorem will work for right triangles, but only right triangles. So only right triangles. All right. So a squared plus b squared equals c squared, recalling that our longest side, c, that is always going to be the hypotenuse. Something else that is also only true for right triangles is SOHCAHTOA, so that is also only right triangles. And this is what will help us find missing sides, or we'll use the inverse ones to find missing angles. So if we're trying to find an angle, so for example, if we've got theta right here, the adjacent side is always the side that's touching the angle, besides the hypotenuse. There's the hypotenuse, always the longest side, and then the other side touching our angle is the adjacent side, and then the side across from that angle is the opposite side. So when we've got SOHCAHTOA, for sine, it's always going to be the opposite over the hypotenuse. When we think of it, it's so S-O-H. For cosine, it's ka, so that will be the adjacent over the hypotenuse. That's C-A-H, so ka. And then lastly, tangent will be the opposite over adjacent, so TOA. And that can help us find missing sides for right triangles. Okay. Inverse trig. So if we do have all the sides, but instead we're looking to find a missing angle, then we'll use inverse trig, and we'll see an example of that in these ones down below. For this first example here, we've got an angle. So the angle we're given is right here. We are given the opposite side, and we are trying to find the adjacent side. So if opposite and adjacent are the sides we're interested in, we'll use tangent, so TOA. So it's going to be tangent of 41 degrees is equal to opposite 4 over adjacent x. So we have options here for how we could solve. Like we could, if we're trying to get x by itself, we could multiply each side by x and then work from there. But since we have a fraction on the right side, something that can also help is just turning the left side also into a fraction. That way we can then cross multiply our two sides. And doing it this way just can help you have a consistent strategy no matter what, because we can always set it up to cross multiply no matter if x is in the denominator or in the numerator. So if I do that, I'll be left here with x times tangent of 41 equals 4. And then from here, if I want to get x by itself, I need to divide by tangent of 41 on each side. And I'm not going to evaluate yet what tangent of 41 is. I'm just going to keep it exact like this as tangent 41, since we don't want to have to round in the middle of our problem. So when we do that, we get, let's see, x equals 4 divided by tangent of 41, and we get, okay, 4.60 for this one. All right, there we are. Okay, so that is how we'd use our regular trig functions to find a side if we're given an angle. On this one here, the information that we're given is we have two sides, and the information that we need is that we need an angle. So we'll also set this one up using SOHCAHTOA. And so we have to think, okay, we've got the hypotenuse and we've got the adjacent side, so A and H, that tells us we're going to be using cosine. So we've got cosine of our angle. Since we don't know our angle, it's going to stay as our unknown here, equals ka A over H, so equals 4 over 5. So here, when our unknown is in the cosine function, the way we kind of undo that is we use cosine inverse. So we can rewrite this problem here as theta equals cosine inverse of 4/5. And so that is how we rewrite it to solve for theta. We could just start directly here if we wanted, but I like just having kind of approaching the start the same way of using just sine, cosine, or tangent and putting whatever missing piece wherever it goes. So here our missing piece was an angle, sometimes it's a side, but we can always start just by using a regular trig function and then use the inverse if we need to find the angles. So here we'll do second cosine and then 4 over 5, and we'll get 36.9 degrees. So theta equals 36.9 degrees. One note is that when we're doing inverse sine and inverse cosine, the input always has to be less than 1. Since the hypotenuse is always going to be the longest side, anytime we do adjacent over hypotenuse or opposite over hypotenuse, we're going to get a number that is less than 1. If we try to do the cosine inverse of a value bigger than 1, like cosine inverse of 2, or anything bigger than 1, our calculator, I think yours will say error of some sort, but it won't work. So that is a sign that something happened earlier in your problem if you're trying to do the cosine inverse of a value bigger than 1. Tangent inverse of a value bigger than 1 will work, because tangent can be the output of the tangent function does not have to be less than 1. Just a note, if you are using a numworks calculator, when you are calculating, when you do the inverse trig functions, so cosine inverse, for example, it's going to say arc cosine. That means the same thing as cosine inverse. So arc cosine of 4/5 gets us the same exact thing that we got in the TI. Okay, moving along here. So we've got angles of elevation and depression. So we're going to do lots and lots of word problems of all of this stuff contextualized. And when we do that, the way the problem will communicate the given information to us is often going to include an angle of elevation or angle of depression. And so what these are, so an angle of elevation is the angle between the horizontal line of sight for someone when they're looking up. So when we look at this person here, their kind of normal line of sight is just looking straight ahead. And then when they look up, that is an angle of elevation. And on the flip side, an angle of depression is the angle between horizontal and the observer's line of sight when they're looking down. Angle of depression is also often a little trickier. We have to remember that we're always measuring from the horizontal line of sight, and so down from there is right here. This angle is not the angle of depression. It is measured from horizontal. All right, so we will see that in an example here. So we've got an eagle sits at the top of a tree at the edge of the ocean while watching a fishing boat. The angle of depression is 24 degrees and the tree is 47 meters tall. How far is the fishing boat from the eagle? Okay, so if we draw this out a little bit here, let's see. So we've got a tree, and then we've got, let's see, a little eagle. Okay. So we know the tree is 47 meters tall, and our eagle is watching a fishing boat. So that, okay, we'll put that here. And the angle of depression is 24 degrees. Okay, so that means this eagle is looking straight ahead. And that means the eagle is going to have to look down to see this boat right here. So 24 degrees is going to be the angle between this horizontal line towards where we're looking. So that would be this angle right here. And we'll notice that if we think about the triangle that we've drawn here, usually just drawing the triangle that's sort of with the right angle on the ground, 24 degrees is not in that triangle. So it's a really common mistake to put 24 in here, but we have to always remember that angle of depression and elevation are always measured from a horizontal line. So we'll think, okay, wait, we need to find the distance between the eagle and the boat. So that distance will be, it's a slanted distance here, but that will be our x. Oftentimes the problems are a little more specific. It'd be like, but the reason I know this is x and not this right here is because the eagle's right here, the boat's right here, this is the distance between them. This is not the distance between them. Sometimes it would say something like the horizontal distance between the bird and the boat. That would be there, or the horizontal distance between the base of the tree and the boat. But since it just said distance, we'll go from the bird to the boat. And if we can either kind of build another triangle here where this distance here would be 47, and then we can use SOHCAHTOA using 24 degrees. Or what you could do is you could figure out what this angle here is, because we know that these two will add up to 90. So if we do 90 minus 24, that will give us 66. So we could use this bottom triangle where we're given the adjacent and the hypotenuse using 66 as our angle. So adjacent and hypotenuse would be cosine. Or if we're using 24 degrees, we are given the opposite side and we're trying to find the hypotenuse. Both will give us the same answer. So if we use 24 degrees, this right here, that would be, okay, we've got the opposite and the hypotenuse, so that would be sine, so sine of 24 degrees equals opposite 47 over hypotenuse x. Again, we can set this up by cross multiplying, so we'd have x times sine 24 equals 47, and then we will divide each side by sine of 24. So we get x equals, let's see, 47 divided by sine of 24. We've got 115.55, so we can call that rounding to 3 sig figs. 116, and then let's see, we're working in context, so meters here would be our answer. Just to show you all what would happen if we used 66, we could still do that. We just have different information now. This would be the adjacent leg, and this is still the hypotenuse. So setting it up that way, we'd have cosine of 66 equals a over h, so 47 over x. Again, setting it up as a fraction can allow us to cross multiply. So we'd have x times cosine 66 equals 47. Divide each side, and we should get the exact same thing. So 47 divided by cosine of 66 equals, 115.55, so rounding to 3 sig figs, 116 meters. So same thing. All right, so what we've got next here is switching gears a little bit into upper and lower bounds. So upper and lower bounds help us figure out what what numbers basically could a number have started at for us to round it to a specific value. For example, we rounded just now 115.55 and on to 116. But if we're just looking at the value 116, it could have been anything as low as 115.5, all the way up to anything before 116.5. Anything below 116.5 still would have rounded to the same value. When we're describing upper and lower bounds, this lower bound, that's what this is. So that is the lower bound. And then this right here is going to be the upper bound. And we will always use these signs here. It's going to be, to describe the lower bound, we're using the less than or equal to sign, and to describe the upper bound, we'll use the less than sign, and that will make a little more sense when we look at our example here. All right, so we've got Jane's weight is 68 kilograms to the nearest kilogram. Determine the upper and lower bounds of her weight. So, okay, I'll use W for weight. We could use X, that'd be fine too. But I want to think, okay, what is the lowest Jane could possibly weigh to still be rounded to 68 kilograms? I know that if she weighed 68.3, oh, no, other way, 67.9, that would round to 68, 67.8 would round to 68, 67.6 would round to 68, 67.5 would round to 68, but anything lower, 67.4, for example, that would round down to 67. So anything that is bigger or equal to, nope, not 64, 67.5. If you equal 67.5, you're rounding up to 68, or if you are bigger than 67.5, you're going to round up to 68. On the flip side, we're going to keep rounding to 68 as long as we are less than 68.5. And I know you might be thinking, wait, 68.5, that would round up to 69, and it would. That's why we're using the less than sign. We're saying you must be less than 68.5. Sometimes something that students try to do, which I'm going to erase this really fast, so don't write it down. Sometimes students will still want to use the less than and equal sign and do 67.4. We don't want to, we don't want to do that because, 68.4. We don't want to do this because that removes like 68.49999. So we just, we want to use the boundaries with 0.5 using the less than sign. So it's always going to be a value with 0.5 and a value with 0.5 on either side. Okay, so Jane's weight could have been anything from 67.5 kilograms to 68.5 kilograms. All right. So the values are always going to end in a 5, but it might not always be directly a 0.5 value, depending on how specific the original question was rounded to. So for example, this one here, we have David ran 100 meters in 11.3 seconds. His time is measured to the nearest tenth of a second. Write the interval within which his exact running time lies. Okay, I'll use T for time. And so we need to think, okay, the value 11.29 also would have rounded to 11.3, 11.28 would have rounded, 11.27, 0.26, everything equal to or bigger than 11.25 will round up to 11.3. So 11.25 is our lower bound. And then our upper bound here is everything lower than 11.35. So yes, 11.35 would round up. So it's everything lower than that. That will round down to 11.3. So again, our values are always ending in 5. It's going to be 0.25 and 0.35 though for this one. All right, last one here. So we have a rectangular garden plot that was measured as 172 by 64 meters. Determine the upper and lower bounds of its perimeter. So for perimeter, that is adding up all the sides. But before we go in and calculate perimeter, we have to calculate the bounds first. So when we do that, our lower bound, or we'll have to do it once for 172 and once for 64. So we'll call this, so the length, we have upper bound of, or we'll do lower first, low to high. Lower bound, if we call, we'll call this one here the length. The lower bound will be 171.5, and the upper bound will be 172.5. So that first measurement could have been anywhere from 171.5 to 172.5. For our width, we'll also find our lower and our upper. So that will be this value right here. So 64 meters could have actually been anything as low as 63.5 meters. And the upper bound could have been anything as high as 64.5 meters, but definitely lower than that. But that's the upper limit. Okay. So when we do perimeter, we have 2 lengths and 2 widths. So we'll have to add these up. So first thing we're going to do is we will use both of the lower bounds to figure out the lower bound. So if the length was as small as possible and then the width is as small as possible, that would be 2 times 171.5, because we could add it twice, but shortcut adding twice is same as 2 times 171.5 plus 2 times 63.5. And so if we do that here, so 2 times 171.5 plus 2 times 63.5, that will give us 470. So that right there is the lowest our perimeter could possibly be. If we find our upper bound the same way, so lower, we use the 2 smallest values. If upper, we use the 2 bigger values. That would lead us to 2 times 172.5 plus 2 times 64.5, and that would equal, we'd have 2 times 172.5 plus 2 times 64.5, and that gets us to 474. So when we write this all out, our perimeter, I'll use P for that. P we know that P could actually be as small as 470, and it definitely will not be bigger than 474. Again, we'll still follow the lower bound could actually equal 470. The upper bound will not actually equal 474, but it could be anything lower. It could be 473.99999. So the way we describe that is using less than 474. One note is that it is really important that we find the possible upper and lower bounds for the dimensions before we do the calculations. For example, if you look over here, if I just did 2 times 172 and then added 2 times 64, so just finding the perimeter using the dimensions I was given, that would get me 472, which if I then found the upper and lower bounds too, for that, it would be 471.5 to 472.5, which is only a difference of, like, the difference between the upper and lower bounds there is only 1. But we see in reality the difference, if we had the lowest length and width to the highest, there's actually a distance of 4 between those. So if we do the calculations first, it makes it look like our options for a perimeter are more specific than they actually are. The perimeter could range quite a bit if each was the lowest it could be or the highest it could be. So very important that we calculate the bounds before calculations. So let's add a little note for here. So calculate bounds before further calculations. Further calculations. That is very important. All right, that is all for today. We'll be on to non-right triangles next time.